Chocolate detained. Reporting back to base.
Let's go!
Wonderful. Send over that video now.
Come on, Panchy, let's get the camera. Why'd we of all people have to do this?
You know I can still hear you, right?
Nah, he means that he wishes we could help you out more, lady.
Lady? A2Gs, tell that bee to watch his tone.
Yeah, our queen is way cooler than yours.
Oh, shut up.
But it's true, though!
I never know how to work this dang thing.
Maybe you should take it off the small tower thing first.
As always, Pachi, your genius never ceases to amaze me.
At your service, Wanchi.
Whatever. Let's just ask one of the engineers.
You know, you could tell me sometimes before you blast off.
Maybe you should pay more attention sometimes.
You mother-
Oh, there he is.
Oh, hello, little ones.
Can you help us get the footage out of this?
Oh yeah, just press this button. Before that though, you guys wanna hear about the catapult?
Sure. Well, I've heard some things about the catapult, especially the trebuchet. You see, the trebuchet was real powerful, and it was really destructive too. Thanks to this, they used it a whole lot in sieges. The big reason why it grew so much was thanks to how many forts there were at the time. It also made it a whole lot easier to flank the enemy. You know, the Germans used it in siege warfare as well. And, they'd use a trebuchet to throw corpses over fort walls. It was one of the first examples of chemical warfare. A big reason why it really became popular was because it could kill a lot of people. At the same time. And thus, with it being able to kill a lot of people at the same time, with more and more people being in a war, more and more people could be killed by the trebuchet. That's actually why it was so much easier for you to flank the enemy during these sorts of situations. Because if you throw a huge boulder into a group of people, they'll have to run away and separate.
Ooh, that's great. You know, the catapult was made all the way back in the year 4 before Christ. Now, don't tell anybody this, but ours is of course more of a trebuchet, which was made the same year. The machine features wedges and levers, and a weight for counterbalance.
I'm gonna be honest with you, Panchy. This dude's insane.
It began to be phased out in the late 1600s, but it was used commonly in ships until the 18th century. At this point, I'm pretty much rambling, but, I mean, you've heard me for this long, right?
Oh, do you now?
And more people to kill. But then it got phased out and more guns were used and wars got so much lamer. Oh, I can continue.
No, you cannot! Get that camera and we are out of here!
I thought you'd never ask.
Yeah, that looks pretty cool, but can you explain how fast the trebuchet throws?
Well, of course I can explain how fast the trebuchet throws, and I'm very thankful that you find it quite cool. First of all, we need to talk a little bit about its measurements because, it's physics, and we have to talk about measurements before anything. So, its height is 0.13 meters, and the mass of the counter rate is 0.025 kilograms, and its acceleration is 9.81 meters per second squared, which is basically gravity. Now, its potential energy is all of those three factors multiplied, so that you get the product, which would be 0.0318825 joules. The potential energy is equal to the kinetic energy, therefore 0.0318825 joules is equal to half of the mass times the velocity. In this case, the mass is 0.025 times the velocity squared, which we don't know. Now, 0.063765 equals 0.025 times velocity squared because we multiplied the previous equation by 2 on both sides. Now we divide it by 0.025 in both sides and we get 2.5506 equals velocity squared. That means that the square root of 22.5506 equals the velocity. The velocity of the throw will be about 1.6 meters per second. That is pretty impressive, by the way.
Yeah, no, I do not understand a single thing of what you just said. But you know what? Let's just move on. Explain the Jenga line, maybe? It looks pretty cool.
Of course you don't understand a thing of what I said, but of course I can explain the Jenga line. Now, we need to talk about its mass, which is 0.0106875 kilograms, and it has an acceleration of 9.81 meters per second squared, which is just gravity. The force of a Jenga block is 0.104844.375 newtons, and the minimum force required to move an object in a static equilibrium is the force of the object times the coefficient of friction. The coefficient of friction for wood is 0.25, therefore the minimum force required to move a Jenga block is 0.25 times its force. which is equal to 0.02621109375 newtons. This means that because the force that is produced by the Jenga block is greater than the force required to move it, a Jenga block will move another Jenga block.
How does a, tiny thing move the huge book? And how's the other book manage to move the even bigger book?
To answer your question about how does that little thing manage to move that bigger book, it is quite simple actually. It is because applying the same process we can realize that the force by the Jenga, which is 0.104844.375 newtons, is greater than the one required to move sketchbook number 1, which would be 0.103005 newtons. So the just set Jenga block will move the sketchbook. Now for sketchbook number 2, it's the same thing. And in the end, we'll notice that because the force that is produced by sketchbook number 1 is superior to the force that is required to move sketchbook number 2, the sketchbook number 1 will move sketchbook number 2. Same thing for the green notebook, as sketchbook number 2 produces 3.6297 newtons of force, and the only require 2.4525 newtons to move the green notebook. The notebook will be moved by the sketchbook number 2. With the binder, it's the same thing. The force required to move the binder is of 2.66985036 newtons, and the force produced by the green notebook is 4.905.
So, how does that cup and ruler thingy work?
Oh, how do the cup and ruler work? Well, this is actually a little bit complicated. The ruler and the cup are quite complex because we have to talk about mechanical advantage here. Now, let's talk a little bit about the height of the ruler, which would be 4.5 centimeters. Now, the cup, which is the most important part, has a mass of 2 grams, and this distance from the fulcrum is of 13 centimeters. Thus, since the ruler acts as a lever, the mechanical advantage would be defined by this. And the distance between both points and the most extreme points in both parts of the ruler is the same. The mechanical advantage equals 1. Thus, the downward force requires to raise the cup is the mass of the cup times gravity, which is 0.002 kilograms, say 9.81, which is equal to 981 divided by 50,000 newtons. The force produced by the binder, which is 13.3492 518 newtons, is greater than this, thus it will raise it. And because the mechanical advantage is 1, and as I previously said, the height of the ruler is 4.5 centimeters, this cup will be lifted 4.5 centimeters. Now the interaction between the Jenga block and the cup is quite simple. The force of the cup while being lifted will be the same that was applied by the binder minus the previous force of the cup. That means that it would be 13.3296318 newtons, and that is greater than what you need to move a Jenga, so it moves the Jenga block. Now, the Jenga block and the DS case and sketchbook and blue notebook, all that.
Okay, wait. Yeah, whatever with levers and all that stuff, but you mean to tell me that moves a Jenga block way bigger things?
You know, this is actually quite simple. It's the same process we applied earlier, and that way we can realize that the Jenga block can move the DS case, that the DS case can move sketchbook number 3, that sketchbook number 3 moves the blue notebook, and the blue notebook is able to move the big sketchbook.
Yeah, okay. That was way too many numbers. How does the ball even stay in place?
Those were not even too many. We're just looking at the whiteboard, my guy. This is actually quite simple to understand. Now, let's talk about the tennis ball, which is actually quite interesting because it's the contrary. We're actually looking at why it cannot move them, and the reason it cannot move them is because its force is of 0.5826379.823 newtons, and what you need to move every other object is more like every other object in that little ramp, which would be the case, the lingua española book, and the big sketchbook. For example, with the case, you need 1.15693254 newtons. For the sketchbook, you need 0.71196.075 newtons, and then for the lingua española book, you need 3.74 newtons.
What about the huge, game cases?
Now, with the Wii case, it's basically the same thing. We can realize the tennis ball has enough force to surpass what is required to move the Wii case, and now the Wii case can move the other Wii case, and then the Wii case can definitely move a Jenga block. I mean, what cannot move a Jenga block? Jesus. And that's how we end up all happy.